So in the last lecture, we have seen the Baire category theorem for compact Hausdorff spaces, and we mentioned that the Baire category theorem also takes into account complete metric spaces. In fact, it states that complete metric spaces are Baire spaces. And so in this lecture, we will define what's a complete metric space, and we will also complete some of the leftover proofs from the previous lecture, which were about the separation properties, the separation lemma for metric spaces, and using both the completeness and the separation properties, we will prove the Baire category theorem for complete metric spaces. So let's start by defining what is a complete metric space. So let XD be a metric space. Then we consider a sequence in this metric space of points, let's say Xn. So this sequence is called Cauchy. This is called a Cauchy sequence if given any epsilon greater than 0, there exists a capital N in the natural numbers such that we have that the distance between xn and xm is less than or equal to epsilon for all n and m greater than or equal to n. So what this means is that the distances of points become smaller and smaller and smaller as you go along the sequence. So in particular, if you take the point xn, this is the capital N here, then the epsilon ball around this BD xn epsilon must contain all of the points xk for k greater than n. So it contains all these points xk for xk for k greater than this capital number n. So this is because in particular we have dxn xk is less than or equal to epsilon. So here we can have the closure as well if you want, and then the equality sign will hold. And so all these points are now clustered around this point x capital N, and with the smaller value of epsilon you take, the closer and closer the tail of the sequence become to each other. So this is what a Cauchy sequence is in a metric space, and a metric space is called metric space XD is called complete if every Cauchy sequence converges. So this is the definition of a complete metric space, and what again this means is that if you have the tail of the sequences becoming closer and closer to each other, then there will be a point to which the sequence converges. Notice that if you assume that xn converges to, let's say, to some point x, then the sequence xn is Cauchy, since if you consider any epsilon greater than 0, the epsilon neighborhood BD x epsilon, so this will contain all points xn for n greater than or equal to some n, some capital N in the maximums. So this is the convergence criteria that we gave. And now, why is this a Cauchy sequence? So I'm claiming that this is a Cauchy sequence. So now I'm going to use this n to prove that dxn xn is less than or equal to epsilon. Well, actually, I can even have it to be strictly less than epsilon here. This is for all n greater than or equal to this capital N. So why is this true? So since xn and xm are points in the sequence, so now I can use the triangle inequality. So this is a proof of the statement before. So I'm going to plug in the point x to which this sequence converges. So dxnx plus dxxm. And now because xn belongs to the epsilon ball centered at x, this means that both of them are less than epsilon. So in fact, I can choose here the epsilon by 2 rather than the radius epsilon by 2 rather than epsilon, and then I will get epsilon in here. So because there is for epsilon by 2 radius, we have chosen this natural number capital N, and now both these dx and x is less than epsilon by 2, and so is dxxm. This is less than epsilon by 2 for all n greater than or equal to n. So this is since xn belongs to dx epsilon by 2 for all n greater than or equal to n. So in particular, for these 2 points xn and xm, if n and m are greater than or equal to n, then both the distances from x will be epsilon at most epsilon by 2, and so this is strictly less than epsilon. So any convergent sequence in a metric space is Cauchy, and the completeness criteria is the converse. It says that every Cauchy sequence must converge. So the completeness criteria is a converse. So before we see some examples of complete metric spaces, let me give a preliminary lemma which gives a sufficient condition for completeness of a metric space. And now we give a sufficient criteria for a metric space to be complete, and this is this lemma here, which says that a metric space XD is complete if every Cauchy sequence has a convergent subsequence. So it is enough for every Cauchy sequence to have a convergent subsequence to claim that every Cauchy sequence converges. So let us look at the proof for this lemma. And so we start with sequence, a Cauchy sequence, be a Cauchy sequence in X, and let epsilon greater than 0 be fixed. So we have to show that xn converges to some point x in X, which means that there exists a capital N such that the distance between xn and x is less than epsilon for all n in n which are greater than this capital N. So this will show that the Cauchy sequence converges. So what is the candidate for this point x? Well, we have a convergent subsequence, and we will show that the point to which the subsequence converges is the required point x. So since xn has a convergent subsequence, say xni, in. So xni converges to x for some point x, and we will show that xn converges to x. So we will show that xn converges to x. So to do this, we use the Cauchy condition. So since xn is Cauchy, there exists an n1 in n such that d of xn is less than epsilon by 2 for all n and m greater than or equal to n1. So here I am taking a strictly less than inequality, but in the definition there was a less than or equal to sign, but it doesn't matter, they are both equivalent. So we can just go with strictly less than. So I want you to convince yourself that having a strictly less than sign is equivalent to having a less than or equal to sign. So now we have this n1, and now take I large enough such that the distance between x and I and x is less than epsilon by 2, and we want ni also to be greater than or equal to n1. So first of all, we choose ni to be greater than or equal to n1, and then we choose a larger ni if required, so that the distance between xni and x is less than epsilon by 2. And this is since xni converges to x. So we can choose such things. And now let us look at the distance between xn and x, and this is less than or equal to dxn xni plus dxni comma x. And we have that if n is greater than or equal to n1 as well, then the first term is less than epsilon by 2 because of the Cauchy condition. So this is the Cauchy condition here. Both ni and n are greater than or equal to n1. So this is by star. And we have the second condition from the convergence of the subsequence. And so the second term is also less than epsilon by 2, and this is from star prime. And so therefore this is less than, this sum is equal to epsilon, and therefore we have that dxn x is less than epsilon for all n greater than n1. So this is n1, and therefore this implies that xn converges to x, and therefore this space is complete because every Cauchy sequence converges. Okay, so now let us look at examples of complete metric spaces and some spaces which are not complete, examples and non-examples. So the first example is just Rn. This is a complete metric space with either the Euclidean metric, which we denoted as D, or the what is called the square metric, which we denoted as rho. So let me just show this for the Euclidean metric, and the proof is very similar for the square metric. So suppose that xn is a Cauchy sequence in Rn, and we have to show that xn converges. So we have to show that xn converges, and we will show that xn has a convergent subsequence. We will show that xn has a convergent subsequence, and so by the lemma above, lemma, this would imply that Rn is complete. So, for the metric D. So, why is this? So, first of all, we prove the first claim is that the set of points xn for which the set of all points in this sequence, if you gather them together in a set, is a subset of some metric ball at the origin and some radius and the closure of it for some r positive. So to show this, we use the Cauchy criterion. So for epsilon equal to 1, there exists a capital N such that the distance between xn and xm is less than or equal to 1 for all n and n greater than or equal to capital N. And this implies that the sequence, the set A, which is the set of all these points in the sequence, is bounded. So how is this bounded? So let us take R to be the maximum of all the distances d, x, xn, xk for all n and k. So n and k less than n. So these are the distances between the first n minus 1 points in the sequence, after which the distance becomes bounded by 1. And this means that the diameter of A under this metric D is less than or equal to r plus 1. This is because D of, if you take any xn and xm, so this is less than or equal to the maximum distance of the first n points in the sequence plus 1. So, and this is less than or equal to r plus 1. So, so we see that this is a bounded set, and this means that the set A itself, the set A, is a subset of the ball of radius r plus 1 and centered at the first point in the sequence, and you can take the closure. So you can take in fact any point in the set A, and because the diameter is bounded by r plus 1, therefore A is a subset of the closure of this set. And this is also a subset of a metric ball with center the origin in Rn and a radius r plus 1 plus the distance between 0 and x1. So there exists some radius for which A is contained in this set, and therefore, so this is the closure. And now we can use the compactness of closed and bounded sets. So this means that xn is a sequence in a compact subset of Rn. This is by the Baire theorem. So by the Baire theorem, these closed Euclidean balls are compact in Rn. Therefore, this sequence is a sequence in a compact subset, and therefore there exists a subsequence xnr, a convergent subsequence of xn by the sequential compactness. So here we can use either compactness or sequential compactness, as we have shown that they are equivalent because Rn is a metric space, and therefore we have a convergent subsequence, and this means that Rn is a complete metric space. So now let us look at an example which is not a metric space. So Q, the rationals with the subspace topology, and well, if you want to view Q as a metric space, so with the restriction, of the metric on R, of the Euclidean metric on R, which is basically the same thing as the subspace topology. So I want you to verify this, that when you consider Q as a metric space on its own by restricting the metric Euclidean metric on R to Q, it is the same as the subspace topology that you get from the standard topology on R. So then this set Q with this topology is with this metric is not complete, and this is because of the fact that you have irrationals in R, and you can take any sequence Qn in Q which converges to an irrational number, say R equals square root of 2, and so then there is no convergent subsequence. Then Qn, in fact Qn, we can say that it does not converge. So this is because you get closer and closer to the point square root of 2, which is outside the set of rationals, and so if Qn converges to some point in Q, that must be a rational point, and we know that this is a Hausdorff space, and therefore you cannot have two limits of the same sequence. So you have uniqueness of limits in the Hausdorff space. So this means that Q is not complete. Another example is R omega. So this is, as you remember, this is the countable product, infinite countable product of copies of R. This is complete. So first of all, we have seen that this is a metrizable space. And this is complete in the metric that you get that you define for this metrizability. So in fact, one of the metrics that one can define is simply the distance function or the metric function. Let me write xn and xyn. So xn yn. This is the supremum of the d bar of xn yn over n, and the supremum is taken over all n. So this is complete in this metric, and this is a result in Munkres. This is theorem 43.4 in my edition in Munkres, and you can see the this proof is quite easy. So remember here that this d bar was just the minimum of dxy, the usual Euclidean metric, and the value 1. So this is a complete metric space. And now we will move to the separation lemma for metric spaces that we promised in the last lecture, and we will show that the Baire category theorem holds for complete metric spaces.